Welcome to TGW plus GWLB architecture. Welcome everyone. Today we're diving deep into one of AWS's most powerful network security architectures, the combination of Transit Gateway and Gateway Load Balancer. This presentation will take you through everything you need to know to implement a centralized, scalable security inspection solution. We'll cover. By the end, you'll have the knowledge and confidence to deploy this architecture in your own environment. Let me start by explaining the problem we're solving and the challenge that led to this architecture. In traditional AWS networking, security inspection had limitations. The TGW plus GWLB combination solves these problems elegantly. Transit Gateway acts as a central hub connecting all your VPCs, while Gateway Load Balancer provides transparent, scalable security inspection. What makes this special is that GWLB preserves the original source and destination IP addresses while distributing traffic across multiple security appliances. This was impossible with traditional load balancers. Let's take a deep dive into the core components. We'll break down each one and understand its role. Transit Gateway. Think of it as a cloud router that can connect thousands of VPCs and on-premises networks. It's managed by AWS, highly available, and scales automatically. Gateway Load Balancer. This is the game changer. Unlike ALBs or NLBs, GWLB operates at Layer 3 and uses Geneve encapsulation to preserve original packet headers while load balancing across security appliances. GWLB endpoints. These are VPC endpoints that create private connectivity between your VPCs and the GWLB service. They act as transparent gateways in your route tables. The beauty is in the simplicity. Traffic flows through these components transparently, getting inspected without complex NAT or proxy configurations. Let's start with a high-level architecture overview. This diagram shows the complete architecture we're building. Let's walk through the traffic flow. Internet traffic enters through the Internet Gateway, is then routed by the Transit Gateway to our Security VPC. In the Security VPC, the Gateway Load Balancer distributes traffic across multiple security appliances running in parallel. After inspection, traffic returns through the same path, and the Transit Gateway routes it to the destination VPC. This creates what we call a security service insertion. All traffic is guaranteed to pass through our security layer. Notice how we have multiple security appliances. This gives us both high availability and horizontal scaling. If one appliance fails, traffic automatically goes to healthy ones. Need more capacity? Just add more appliances. The red Transit Gateway is our central hub. The blue Security VPC contains our inspection layer. And the green Gateway Load Balancer ensures optimal distribution and health checking. Internet to VPC traffic flow. Let's trace a packet from the internet to your application. This is probably the most common traffic pattern you'll be securing. An external user sends a request that hits your internet gateway. The IGW forwards it to Transit Gateway, which consults its route tables. Based on our configuration, TGW routes the traffic to the Security VPC. In the Security VPC, the packet hits a GWLB endpoint, which forwards it to the Gateway Load Balancer. Here's where the magic happens. GWLB encapsulates the original packet in Geneve and sends it to one of the security appliances. The security appliance performs deep packet inspection, threat detection, or whatever security functions you've configured. If the traffic is clean, it's returned to GWLB, which strips the Geneve encapsulation and sends it back through the Security VPC routing. Finally, Transit Gateway receives the inspected traffic and routes it to the target VPC where your application receives the request, completely unaware that inspection occurred. VPC to Internet traffic flow, egress. Egress inspection is equally important and follows a similar but reverse path. Your applications often need to call external APIs, download updates, or access cloud services. When an application in VPCA makes an outbound request, it goes to Transit Gateway first. Our route tables force this traffic through the Security VPC for inspection. The same GWLB process occurs. Traffic gets load balanced across security appliances where you can implement controls. After inspection, traffic flows back through TGW to the Internet Gateway and out to the destination. Your applications receive their responses through the same inspected path. VPC to VPC communication, east-west. This is where the architecture really shines for security. East-west traffic inspection between VPCs is often overlooked but critical for preventing lateral movement during security incidents. When VPC A needs to communicate with VPC B, instead of direct routing, we force traffic through our security inspection layer. This enables micro-segmentation at the network level. The bidirectional flow shown here is important. Both the request and response get inspected. This ensures complete visibility and control over inter-VPC communications. Use cases include the best part. Applications don't need any changes. This is purely a network-level implementation. Implementation Strategy Overview. Before we dive into commands, let's understand the implementation flow. There are clear dependencies we must follow. You cannot create a GWLB without target groups, and you cannot create endpoints without an active GWLB service. I've organized this into 4 phases. Foundation phase. Build the basic networking infrastructure, VPCs, subnets, and security groups. Transit gateway phase. Deploy TGW, create attachments, and set up the initial routing framework. Security infrastructure phase. Launch security appliances, create target groups, and deploy the gateway load balancer. Connectivity phase. Create GWLB endpoints, and configure the final routing that steers traffic through our security layer. Following this sequence prevents configuration conflicts and ensures each component is ready when the next phase needs it. Transit Gateway Route Tables Strategy. Route tables are the brain of this architecture. Let me explain the strategy that ensures correct traffic steering. We create separate route tables for different purposes. Security Route Table, associated with the Security VPC attachment. This table contains routes that direct inspected traffic to its final destinations. Workload Route Table, associated with Application VPC attachments. These tables ensure all traffic passes through the Security VPC first. Internet Route Table, for Internet-facing attachments, to ensure all Internet traffic is inspected. The key insight is that we're creating a hairpin routing pattern. Traffic always goes through the Security VPC, regardless of source and destination. This guarantees inspection while maintaining the flexibility to bypass inspection for specific traffic if needed. Creating the foundation means setting up VPCs. Now, let's get hands-on with the actual implementation. We start by creating our Security VPC, which will house all of our security infrastructure. I'm using the 10.0.0.0/16 CIDR block, which gives us plenty of IP addresses for multiple availability zones and future growth. You might choose different CIDRs based on your network design. The key thing here is planning your IP addressing scheme carefully. The Security VPC needs to accommodate. Notice how we're tagging resources immediately. In production environments, proper tagging is crucial for cost allocation, automation, and compliance. Building the central hub, Transit Gateway. The Transit Gateway is the heart of our architecture. These options might look technical, but each one is important for our use case. Amazon side ASN, we're using 64512, which is in the private ASN range. This matters if you're connecting to on-premises networks via BGP auto-accept attachments, enabled for convenience in our setup, but in production you might want manual approval for security. Default route table settings. We're enabling these initially, but we'll create custom route tables for our traffic steering logic. One thing I love about Transit Gateway is that it's fully managed. AWS handles all the underlying infrastructure, scaling, and availability. You just configure the routing logic. The creation process takes a few minutes, so this is a good time to prepare your next steps or grab coffee. Connecting VPCs to Transit Gateway. VPC attachments are how you connect your VPCs to the Transit Gateway. Each attachment creates elastic network interfaces, ENIs, in the subnets you specify. When selecting subnets for TGW attachments, choose one subnet per availability zone for high availability. The subnets should be dedicated for TGW use, or at least have enough free IP addresses. Here's a production tip. Create dedicated transit subnets in each VPC specifically for TGW attachments. This makes IP management cleaner and provides better security isolation. The attachment creation is usually fast, but the ENIs need a few minutes to become active. You can verify the attachment status with describe commands. Remember to create attachments for all VPCs that need to communicate through this architecture, including both workload VPCs and the security VPC. Custom route tables for traffic control. Now we create custom route tables to implement our traffic steering logic. The default route table isn't sufficient for our security inspection requirements. Why separate route tables? Because we need different routing behavior for different VPCs. The creation command is simple, but the magic happens when we associate VPCs with these tables and configure the routes. That's where our traffic steering logic gets implemented. Think of route tables as traffic controllers at an intersection. They decide which direction traffic goes based on the destination. Launching security appliances. Security appliances are the workhorses of our inspection layer. The choice of instance type and AMI is crucial for performance and compatibility. For instance types, I recommend compute-optimized instances like C5, large or larger for production workloads. Network-optimized instances like C5N or C6GN might be even better for high-throughput scenarios. The AMI should be from your security vendor, whether that's Fortinet, Palo Alto Networks, Checkpoint, or others. These vendors provide GWLB-ready AMIs that support GENEVE encapsulation. The user data script is critical. It should configure the appliance to launch appliances in multiple AZs for high availability. Start with at least 2, but plan for horizontal scaling based on traffic patterns. Creating target groups for GWLB. Target groups for Gateway Load Balancer are different from those used with ALBs or NLBs. The protocol must be Geneve, and the port is typically 6081. Health checks are crucial here. Your security appliances must implement a health check endpoint that GWLB can monitor. This could be a simple HTTP endpoint that returns 200 when the appliance is ready to process traffic. The health check parameters I'm showing are conservative 30-second intervals, 5-second timeouts. In production, you might tune these based on your appliance startup times and processing characteristics. Key insight: unhealthy targets are automatically removed from rotation, so make sure your health checks accurately reflect the appliance's ability to process traffic, not just its running state. Geneve is essential because it's how GWLB preserves the original packet information while routing to your appliances. Registering security appliances. Registration associates your security appliance instances with the target group. This is when GWLB starts monitoring their health and preparing to send traffic. You can register multiple instances at once, as shown in the command. Each instance ID represents a security appliance that can process traffic. After registration, check the target health using the describe target health command. Don't proceed until your targets show as healthy. This usually takes a few minutes while the health checks complete. In production, consider using auto-scaling groups to manage your security appliances. This allows automatic replacement of failed instances and scaling based on demand. Pro tip: set up CloudWatch alarms on target health metrics so you're notified immediately if appliances become unhealthy. Now we create the Gateway Load Balancer using our healthy target group from the previous step. Remember, we confirmed our security appliances were showing healthy status in the target group. The Gateway Load Balancer is fundamentally different from ALBs or NLBs. It operates at Layer 3 and uses GENEVE encapsulation to preserve original packet headers while distributing traffic. Notice the gateway type. This is the key parameter that creates a GWLB instead of other load balancer types. The internal scheme means this LB isn't internet-facing but designed for private connectivity through VPC endpoints. We're deploying across multiple subnets in different AZs for high availability. If one AZ has issues, traffic continues flowing through others. The creation takes several minutes as AWS provisions the underlying infrastructure. Once complete, we'll get an ARN that we'll use in the next step to create a listener. Creating the load balancer listener. Now we will create a listener using the Gateway Load Balancer ARN from the previous step. The listener defines how the GWLB processes incoming traffic. Unlike ALB or NLB listeners with complex rules, GWLB listeners are straightforward. They have a simple forward action to the target group we created earlier. The listener references our target group ARN containing the healthy security appliances. GWLB automatically handles load balancing using 5-tuple hashing for flow stickiness. Flow stickiness is crucial for stateful security appliances. The 5-tuple hash, source IP, source port, destination IP, destination port, protocol ensures packets from the same flow always reach the same appliance. Once the listener is created, our GWLB is ready to process traffic, but we still need to make it accessible through VPC endpoints. Now let's create a VPC endpoint service. We create this service using the Gateway Load Balancer ARN from our previous steps. This service makes our GWLB consumable by other VPCs through private endpoints. It acts as a bridge, allowing workload VPCs to connect privately to our security inspection layer without traversing the internet. For security control, I'm setting acceptance required to true. This means that when other VPCs try to connect, we have the opportunity to manually approve those connections. The service will generate a unique service name, like COM Amazonas, VPCE region VPCE SVC XXXXX. We will use this name when creating GWLB endpoints in our workload VPCs. This approach enables secure private connectivity and supports cross-account sharing if you need to provide security services to other AWS accounts. Creating the VPC endpoint service. The VPC endpoint service is what allows other VPCs to connect to your gateway load balancer privately. Think of it as making your GWLB consumable by other VPCs. The service name generated, COM Amazonas, VPCE region, VPCE SVC XXXXX, is what you'll use when creating VPC endpoints in your workload VPCs. For security, I've set acceptance required to true, meaning connection requests need manual approval. In production environments, this gives you control over which VPCs can access your security services. The service type, Gateway Load Balancer, tells AWS this is specifically for GWLB integration, not for other services. Once created, this service can be shared across multiple AWS accounts, making it possible to provide security services to other teams or business units. Creating GWLB endpoints. GWLB endpoints are the final piece of the connectivity puzzle. These VPC endpoints provide private access to the Gateway Load Balancer service from your workload VPCs. Each endpoint gets a network interface in the subnet you specify. This ENI has an IP address that you can reference in route tables to steer traffic through the security inspection layer. The endpoint type Gateway Load Balancer is specific to GWLB and creates endpoints that can be used as targets in route tables. This is something regular VPC endpoints cannot do. For high availability, create endpoints in multiple AZs. If you have workloads in 3 AZs, create GWLB endpoints in all 3. These endpoints appear as ENIs in your VPC, and you will reference their IDs in route table entries to direct traffic through them. Implementing traffic steering routes. This is where the magic happens. We configure routes that force traffic through our security inspection layer. In workload VPCs, we create a default route, 0.0.0.0/0, that points to the GWLB endpoint. This means all traffic from this VPC will go through security inspection first. The beauty of this approach is its simplicity and completeness. There's no way for traffic to bypass inspection because the routing makes it impossible. In the security VPC, we configure specific routes that send inspected traffic to its final destinations via transit gateway. These routes are created after inspection is complete. The route table configuration is what implements our security service insertion architecture. Every packet must pass through the security layer to reach its destination. Advanced configuration options. Let's talk about some advanced configurations that can optimize your deployment for production use. Cross-zone load balancing ensures even distribution across all AZs, preventing hotspots. This is especially important if your security appliances have different capacities or if traffic patterns vary by AZ. Health check tuning can significantly impact your architecture's behavior. Shorter intervals mean faster detection of unhealthy instances, but more overhead. Longer intervals mean slower failover but less health check traffic. Consider implementing custom health checks that verify not just that your appliance is running, but that it's actually capable of processing traffic according to your security policies. Flow stickiness is automatically handled by GWLB using 5-tuple hashing, but you can influence this through your network design and security appliance configuration. Monitoring and troubleshooting. Monitoring is crucial for maintaining a healthy security architecture. These commands show you how to check the health of your components. Load balancer status should always show active in production. If it shows provisioning for more than a few minutes, check for configuration issues. Target health is the most important metric. Unhealthy targets mean reduced capacity and potential single points of failure. Set up CloudWatch alarms for this. I recommend creating a monitoring dashboard. Don't forget about the security appliances themselves. Monitor CPU, memory, and application-specific metrics to ensure they're not becoming bottlenecks. Security best practices. Security doesn't end with deploying security appliances. The infrastructure itself needs to be secured properly. Security groups should follow the principle of least privilege. Only allow the traffic that's absolutely necessary for proper functioning. Encryption in transit is important for management traffic. Use SSL/TLS for appliance management interfaces, and consider VPN or AWS Systems Manager for administrative access. Logging is crucial for both security and compliance. Enable VPC flow logs, CloudTrail, and ensure your security appliances are sending logs to a centralized system. Regular updates of security appliances are critical. Coordinate with your security vendor for updates and plan maintenance windows appropriately. Backup configurations, and have a disaster recovery plan. Document your architecture and keep configuration backups for quick recovery. Let's look at cost optimization strategies. This architecture can be cost-effective when properly optimized. Let me share some strategies I've used in production. Right-sizing instances is crucial. Monitor CPU and network utilization to ensure you're not over-provisioning. Start conservative and scale up based on actual usage. Auto-scaling can significantly reduce costs by scaling appliances based on demand. Use CloudWatch metrics like processed bytes or target utilization to drive scaling decisions. Consider using spot instances for non-critical security functions or development environments. For production, stick to on-demand or reserved instances for predictable performance. Monitor GWLB processed bytes charges carefully. This is typically the largest cost component. Optimize your routing to avoid unnecessary traffic through the inspection layer. Review and optimize route tables regularly to ensure you're only inspecting traffic that actually needs inspection. Implementation Roadmap Summary. This final diagram summarizes our complete 14-step implementation process. Each phase builds upon the previous one, and the dependencies are clearly marked. Phase 1 Foundation creates the basic networking infrastructure. You can't proceed without solid VPCs and subnets. Phase 2 Transit Gateway establishes the central routing hub. All VPC attachments and route tables depend on this. Phase 3 Security Infrastructure deploys the actual security components. Target groups need healthy instances, and GWLB needs target groups. Phase 4 Connectivity ties everything together with endpoints and final routing configuration. Phase 5 Testing is crucial. Validate every traffic flow before declaring the implementation complete. Following this roadmap prevents configuration conflicts and ensures each component is ready when the next phase needs it. I've seen implementations fail because teams skipped ahead or didn't wait for components to become fully available. Key takeaways and next steps. Let's wrap up with the key points that will make your implementation successful. First, this architecture provides comprehensive security coverage. All traffic flows through your inspection layer. There are no blind spots or bypass routes. Second, it's highly scalable and resilient. You can add security appliances for capacity and remove failed ones without disruption. Third, it's operationally simple once deployed. The complexity is in the initial setup, but day-to-day operations are straightforward. For next steps, I recommend starting with a proof of concept in a development environment. Test all traffic patterns thoroughly before moving to production. Consider automating the deployment using infrastructure as code tools like CloudFormation or Terraform. This makes deployments repeatable and reduces configuration errors. Finally, engage with your security team early and often. They need to understand the traffic flows and configure the security appliances appropriately for your environment. Thank you for your attention. I'm happy to answer questions about any aspect of this architecture.